Welcome to Lesson 11C, Particle Settling in a Container. We're going to talk about gravimetric settling of particles in a container. This can also be applied to a room, and I do this in ME 405 when I teach about indoor air quality. We're talking about rooms. Here we'll talk about containers, but the fundamentals we learn here are applicable to several other things, so I need to talk about this first. We'll also describe differences between laminar and well-mixed settling and do two example problems today. So just a quick review, these are the equations for terminal settling speed of spheres in quiescent still air. So here's our VT equation, and then of course you're used to doing this by now. We have to calculate mean free path, Newton number, Cunningham correction factor, Reynolds number, drag coefficient, etc., iterate, and we get VT for any given air conditions and particle properties. So you already know how to do all that. And a quick review of our terminology. Monodispersed aerosols mean that all particles are of the same size, and polydispersed aerosol means particles are a range of sizes. So as we've done before, we consider one particle diameter at a time. So we're doing a monodispersed calculation, but we can apply this to polydispersed aerosols since we're treating one particle at a time and they don't interact with each other. Let's consider laminar settling in a container or a room for this monodispersed aerosol. Assume that we initially have well-mixed particles, as I sketched here. So these are just randomly distributed particles throughout the volume of a container. Container has height h, and each particle is falling with some speed vt, terminal settling speed. Note that I dropped the j subscript, so instead of cj, we're just going to call that c from now on, since we're always dealing with just one substance. Or we can deal with multiple substances, but we only treat one at a time. So what happens in this case? Well, the particles start falling, and you end up with kind of an interface here where everything above here is clean air, and everything below is still the same concentration that we had, C naught. These particles start settling to the floor also. This is at t equals 0, first one, and then the next one's at some time t1, and then sometime later, this interface has moved down even further. And the key is that that interface is also moving at speed vt, because the particles at the very top are moving at vt, and they have had a chance to move all the way down here from the top. All the other ones are moving at vt uniformly. So basically this entire chunk of particles is moving down as a unit. And so you end up with clean air at the top. And as you go on in time, the clean air portion gets bigger. By time t2, it's about half of the container, and all the particles are in the bottom, and then some of them have settled down at the bottom. So we assume that when the particles hit the bottom of the container, they stick there. We're not allowing for any resuspension of these particles. We also assume that the particles don't interact with each other, as we've always been making that assumption. Well, the algebra is pretty simple here. For this case, we say that H1 is equal to Vt times T1. And similarly, H2 is Vt times T2. So we can make a more general statement. H being the distance from the top of the container is Vt times T. By the way, we all know that this happens. If you've ever dusted, you know that dust just kind of builds up on furniture and other flat surfaces. The dust just settles and sticks there on surfaces. Now this process will continue until C equals 0. In other words, all the particles are on the bottom. Obviously, that'll be some time later than T2 as I have drawn here. In fact, it should be about twice T2 because it's halfway there at my time T2, this third picture here. Now I can plot h as a function of time. Remember, h is the height from the top of the container. So initially it's 0, and this is a linear equation. So h just grows with time until little h is equal to capital H, which means that we're completely clean now. All we have is clean air, and all the particles are on the bottom of the container. Let's call this Tc, which we'll call the critical time. The time it takes for all the particles to fall to the bottom of the container. And beyond that time, the air is perfectly clean. From this graph, you can see that the equation is just Tc is h over Vt. This is what we call laminar settling, where there's no mixing of the air. This would be an extreme case where there's no mixing at all. Examples might be in a closet where there's no ventilation and no air moving around, or in a sample container where you're trying to measure particle distribution. So you grab a sample like a container of air with particles, and then you just let it sit there. Let's define the average concentration. Remember, we've dropped the C subscript. Well, if you think about it, the concentration in the upper portion is 0 times distance h plus the initial concentration times h minus h, which is the bottom of the container, and then that whole thing divided by h. How did I get that? Well, let's look back at our diagram. Let's take this third case here where you have about half of it clean and half of it dusty. I take the top half that has a concentration of 0 and I add that to the bottom half that has a concentration of C0, and I average those two together depending on the height. So this is the equation I end up with. This is good at any time, t. That first part is the upper portion with the clean air, and the second part is the lower portion with the dusty air. Well, the first term is just zero, so C average is just C0 H minus H over capital H. Or since little h is VTT from previously, this is C0 times H minus VTT over H. Non-dimensionally, we just divide by C0. So we get C average over C0 is 1 minus VT over H times T. Finally, let's define this as 1 over Tc. So Tc is the critical time, which is H over Vt, as we had already specified up here from our diagram. So this equation finally becomes C average over C0 is 1 minus T over Tc. Now technically this is valid only for T less than Tc, because once you reach Tc, C average is 0, the air is perfectly clean. So we have to do two parts to this equation, and that is that C average over C0 is 0 when T is greater than or equal to Tc. So this is our summary equation set for laminar settling in a container for monodispersed particles. Remember that we can also have other particles in there at the same time. If these particles don't interact with each other, we can have other particles of different diameters, different settling speeds. But all the ones with this particular Vt are grouped together in one monodispersed aerosol in our equations here. We've already talked about removal efficiency when we briefly talked about air cleaners, when we talked about emission factors and things like that. Let's define removal efficiency as eta. We've already defined eta as 1 minus C out over C in whenever you have some kind of an air cleaner with air coming in, same volume flow rate of air coming out, dirty air coming in, less dirty air coming out. Here, eta is a function of time because this is an inherently unsteady process. We have all these particles settling with our interface up here. So here, eta as a function of time is 1 minus C average over C0. Remember, the average is average over the whole container. C0 is this initial concentration, which is there everywhere under the interface. Well, we have expressions for C average over C0 depending on whether it's before or after the critical time. So let's just throw those into here. When T is less than critical time, eta is 1 minus C average over C0 is equal to 1 minus T over Tc from here. Plug that in, and we get T over Tc. When we plug in our expression for Tc, this becomes VTT over H. If T is greater than or equal to Tc, eta is 1 or 100% because all of the particles have been removed. Remember, this is a removal efficiency, so 100% means all the particles have been removed. So this is the removal efficiency for laminar settling in a container, and it's a two-piece equation because once it hits critical time, then it's 100% from there on. Let's do an example problem. At time t equals 0, we have well-mixed dusty air at SATP in a closet. The height of the closet is 2.4 meters. There's no ventilation, nothing stirs up the air, so it's quiescent air. Dust particles of diameter 2.5 microns, given density, are under consideration. The initial mass concentration is 68.9 microgram per meter cubed. And we want to estimate the average mass concentration after 2 hours have passed. We're going to assume laminar settling, assume that all particles that hit the floor remain there, they stick to the floor, and we want our answer in microgram per cubic meter. So we need to calculate VT. We already know how to do that. Use all our equations to get rho, ideal gas law, mu from Sutherland, and lambda from the mean free path equation at our given temperature and pressure. We happen to be at SATP, so we can just get those from the equation sheet as well. Use the Knudsen number and the Cunningham correction factor equation just to verify your answers. I get 1.0674 for Cunningham. And then you iterate using your software to get VT. I'll give 4 significant digits here. I get 0.0002848 meters per second. It turns out that since these particles are so small, and they have a small density too, that Stokes' approximation is actually very good for this particular case. But I just throw it into my iteration scheme anyway since I have it set up, and you should do always the same. The critical time is H over VT, and that gives us 8426.8 seconds. Our T is 2 hours, so we got to do some unit conversions. There's 3,600 seconds per hour, so we have 7,200 seconds, which is less than TC, 8,400 seconds. If it were greater than TC, our answer would be 0. We'd have no concentration because the air would be perfectly clean. So here we're going to be able to use the top portion of this or the top portion of this equation. We'll actually use this one because we're after the average concentration, not the efficiency. So this is the equation we use, and I plug in the numbers and their units. The initial concentration was given as 68.9 microgram per cubic meters, and then we have 1 minus the ratio of these two times. I'll put both of them in seconds, and I got 10.0 microgram per cubic meter as my answer. Keep in mind that what we mean is that we started at about 68.9. At 2 hours, most of these particles have settled. There's an interface here, and a lot of particles have ended up on the floor. And then this C average is the average of this portion, which is clean air, C equals 0, and this portion, which has C equals C naught. So that's our answer. Now let's look at well-mixed settling in a container. Now the laminar case was one extreme, as I pointed out. This well-mixed case is another extreme. This is the exact opposite, also called turbulent, but I really don't like that term because it really is well-mixed. Turbulent just means that there's some fluctuations in the room and then the particles would settle at an average of VT like we talked about. The air can be turbulent but not well-mixed. So well-mixed, as we talked about with flux chambers, means that we imagine having a ceiling fan in this container or room, which is constantly stirring up the air. So the air is certainly turbulent, but it's also well-mixed, meaning that particles will kind of travel with these eddies and move up and down all over the place. But they're also settling with time. So this is a little harder to sketch, but let's look at two different times. At t equals 0, we have a random distribution of aerosol particles uniformly distributed. At some later time, we have still uniform distribution, but there are much fewer particles because some of them have settled out. So this is our initial concentration, C naught, and this will be our concentration at T1. Notice that it's still uniform, it's well mixed. So C at any location, if you're here or here or here or here, C is the same. It's just smaller than C naught because some of these particles have started to settle. By the way, even for this case, we're making the assumption that when the particles hit the bottom of the container, they stick there. Well, if you do the math, and I'm not going to go through all the details, it's pretty simple, but it turns out to be a first order ODE for C as a function of time. I'll just give you the solution. C over C naught is exp, exponential function, to the negative VT, T over H exponent. Or again, defining this as 1 over TC, this becomes exp of negative T over TC. This will be an exponential decay that theoretically never hits 0, but it asymptotes to 0. So we don't need a two-part equation like we did with the laminar case. In summary, C over C naught is exp negative T over TC. And then eta, the removal efficiency, is 1 minus C over C naught. This will be a function of time. So it's just 1 minus exp negative T over TC. So that's the equation for well-mixed settling. I want to just show you these two extremes on a plot. If we plot C as a function of time, both the laminar and the well-mixed cases start at C naught. The laminar one decays linearly to the critical time. The well-mixed one decays exponentially and goes to 0 at infinity. So these are two extremes. Nothing's ever perfectly well-mixed. You literally have to have a ceiling fan and fans all over the place just stirring everything up constantly. Laminar, you can sometimes obtain that if you have a container and there's no motion at all. But in real life, we're probably somewhere in between these two extremes. Let's do an example problem. This is exactly the same problem I had before, except now we're going to assume well-mixed. It's all the same numbers that we had in the previous example. So it has the same density, viscosity, lambda, C, VT, etc. as previous example. Recall for the laminar case, we had C equal 10.0 microgram per meter cubed after 2 hours. For the well-mixed case, we have to apply C equals C naught, exp negative T over TC. I just want to mention here that this TC is the same TC as in the laminar case, even though it's not as physically significant as it was in the laminar case, but we use the same TC that we had already calculated. So the rest is just plugging into the numbers. C of T at 2 hours is the initial C naught times exp to the negative T, 7,200 seconds. TC is the same one as before, also in seconds, so they cancel out. I want to caution you, not just for this course, and I've mentioned this before, anytime you have a natural log or an exp of something, these guys in brackets here have to be non-dimensional and unitless, so don't make that mistake. I plug in the numbers and get 29.3 microgram per meter cubed for the well-mixed case. Just one comment, notice that compared to the 10 that we had for the laminar case, this is bigger. Why is that? Go back to our sketch. You can see that at some time, let's just pick some arbitrary time here, the well-mixed case has a higher C than the laminar case. Also note that for the laminar case, this is the average C, whereas for the well-mixed case, it's the same C either way because it's well-mixed. It's uniform throughout the container. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.